Now, the first thing that we're going to look at is the notion of linear data structures, stacks, queues, and priority queue. Now, why do we call it linear? We call it linear because it kind of works as a line. But the important thing here is that you cannot do it with random access. If you want to get some element from the line, you can, but it has to be a specific element. That means you cannot reach out to any part of the line. Now, what do we mean by that? Let's take a look at a stack, right? So only one data element is accessible at any point of time. Now, let's say you're given a stack of plates. Now, can you take anywhere in the middle, right? So you can take something from the middle, but it's not going to be convenient, because what you have to do essentially is to take everything out first on top of it. You take the middle one, and then you put everything back, which means that this operation is not so easy. Now, on the other hand, a stack essentially is defined by a certain form where you put the new things on top, and when you need to take something out, you also take it from the top. So, for example, so this is a stack, and we call it LIFO, or last in, first out. So which means that the last thing that you put in is going to be the first thing that you take out. Now, they are defined by three main operations, and we're going to define this tree. And when we say abstraction, what it means is that we're just going to define what they do. Now, how they do it is a matter of implementation. We will discuss that a little bit, but the focus of the course essentially is on how to apply them to solve problems. So it means that when you learn about stacks, queues, and so on, what we want you to do is to figure out, can I put it into some of my algorithms? Can I use a stack, can I use a queue to solve some of the problems that we have? Now, a stack is defined by these three operations. The first one, okay, so we're going to talk about the specific operations later, but let's take a look at some examples of the applications of a stack. Now, these are real examples of stacks, like a toy, right, tower of a toy, stack of coins, books, and so on. Now, there are some actual applications of the stack. We don't always think of it that way, but they actually use stack underneath. And for example, one of them is a backspace key. So when you type on your computer, you're going to type one letter after another. And at some point, when you decide to remove some letters, you are going to type backspaces. And the backspace, you don't need to point to a specific letter. The backspace knows which one you want to remove. And that is going to be the most recent one that you type. So for example, if you type the following sentence, so essentially there is a stack from the bottom to the top, and when you click on type on backspace, it's going to remove the last one, which is the G, and that's essentially the top of the stack. Now you can also do this with the undo operations. So you do certain things on your computer, and you decide to undo, right? So when you undo it, it's going to return back to the most recent thing that you did. And so meaning that the computer has to maintain this kind of sense of recency, like which one did you put in the last. Now, something that you may not notice, but it's actually something that's happening all the time in the computer, is what we call a function called stack. And the idea here is that a function may call another function, which may again call another function. And there is a certain sequence in which these functions need to be processed for them to process it properly. So for example, in this case, f1 return 2 times f2, which means that it needs the value of f2 before it can return. So when it calls f2, f2 in turn calls f3, f3 in turn calls f4. Now in this case, f4 doesn't call anything, so it can return. But along the way, when f1 calls f2, f1 has to wait. And when f1 is waiting, it's going to enter into a stack. Now, as f1 is waiting for f2, f2 goes into the stack because it needs to wait for f3. f3 needs to go into the stack because it needs to go to f4. Now, essentially what this is telling the computer to do is to execute f4 first. Because if it doesn't finish f4, nothing is going to be done. Because f3 depends on f4, f2 depends on f3, f1 depends on f2. So this, once the computer has time, is then going to focus on finishing f4 first. It takes it from the top of the stack. Do that. Once it's done, then it can then go on to the next one, which is f3. And when it's done, it goes on to f2, f1, and finally, then it's all going to be done. Now, this may cause certain problems that we call Stack Overflow. Now, this, of course, this also is the name of a famous website, right? So, so the website essentially is inspired by this programming problem, because this is a pretty common problem. Especially if you start writing recursion and so on, you will start to realize that sometimes your method will go out of stack, like Stack Overflow. basic idea here is that the computer is going to maintain some memory space to contain the stack. So as we are doing all these function calls, it's going to retain what are the sequences of the function calls that you need to do, which means that at some point, if you keep calling more and more functions infinitely, at some point it's going to overflow, meaning that it is going to overreach, it's going to go beyond what is the space that you allocate for it. Now in this case, for example like here, if you have a Stack Overflow, now it looks like recursion. A calls A plus 1, A plus 1 calls A plus 2, and so on. But because it keeps going up, so 1 calls 2, 2 calls 3, 2, 4, 5, 6, and so on, it's going to go on infinitely. At some point it's going to overflow, and when it overflows, it's going to crash. Now, though it looks like recursion, strictly speaking, it's not recursion, because when you say recursion, it will call itself, and it has to reduce. And the whole point about reducing is exactly that, because if you don't reduce, it will never end. If it doesn't terminate, then it's not actually a valid algorithm. Now, there are 3 operations for a stack, and they are defined in terms of, in abstraction. It means that you can define them without saying how they're going to be implemented. So here, for example, is the push operation. Now, you can create a stack, you can push some things onto the stack, and every time you push something, it's going to go to the top of the stack. So if your stack currently looks like this, orange the top, gray below, you push a new thing, which is kiwi, kiwi then is going to go to the top of the stack, so that the top is now kiwi. For peak, peak means that we want to know what is the item at the top, but we're not going to remove it. Okay, for pop, we are going to take the top element off, we return that, and after the operation, essentially the top is now going to be the next one, which is orange, because the previous top is going to be removed. Now, the application of this to motivate why is it that we want to do something like a stack is because it's going to make solving some problems easier. Now, let's take a look at one example problem that we can solve using a stack. So this is parenthesis, right? Parenthesis like this opening and closing. It's common when we get a mathematical expression. And every time we close, every time we open, we have to close it at some point. And it gives it meaning. So for example, A plus B, you put parentheses around it. It means that you have to do this operation first before you do the multiplication. Now, braces are used in programming languages, for example, Java. So in this case, you have an opening brace, you have to close it. Now, if you have any problem with the braces being imbalanced, that means you open one up, you don't close it, or you close something you never open, it's going to cause any problems in the operations. So the compiler, when it reads your programming language in Java, it tries to produce a working code, it needs to check for these things. Now, how do we check for this? Now, of course, you can write a program to do this. Now, if you are using a stack, this program can be expressed very simply. And the key idea here is that when you close a brace, you are closing an opening brace. But which opening brace did you close? You close the most recent one that you opened. So for example, let's say you have the following statement, right? So you open once, you open twice, and then you close. Now this closing, the first closing actually closes the second opening. And the second closing is going to close the first opening. Which means that it's going to mimic essentially the operation of a stack, because every time we close, we want to close the most recent one. The most recent one that actually goes onto the stack. So if we follow this logic, then we can do the following things. So every time we can go from left to right, when we encounter an opening brace, we put it into the stack. So it's kind of like saying, here is an opening brace that at some point we need to close. Now we just keep going. Every time you meet an opening brace, you just put it into the stack. Now when you meet a closing brace, so this is going to remove one of the opening braces that you have in the stack. And you just need to say pop. Now when you pop it, what happens is that it's going to pop the most recent one. And the most recent one is exactly the one that you actually put in. So now if at the end of the day, your stack is empty, it means that your braces are balanced, because everything that you put in, you take out. So there are no odd braces there. So for example here, there are 2 opening, 1 closing. So you push 2, but you pop 1. But in that case, then it's going to be an error, because in that case, it means that you have not closed one of the braces. Now, you can also come into a situation where the braces are balanced, but they are out of sequence. So in this case, you close before you open, so that's wrong, right? So which means there is some imbalance. Now, how do we detect that? Now, if this happens, at some point, you are trying to pop, because every time you close, you're going to pop, but you're going to pop something that's empty. So when the stack is empty, when the pop is done, it means that there is some imbalance within the method. So then if you write it inside a code, right, it actually just runs as small as this. So you have a word, for example, a text. Then you create a new stack. For every letter in the text, if it's an opening brace, you push it. If it is a closing brace, you first make sure that it's not empty, then you pop it. Then if at the end of the day, it's all balanced out, then you return true. So something like this could actually be done without a stack. But you can imagine it's probably much more complicated than doing this with a stack, because the stack essentially encapsulates the logic of taking the most recent thing out first. Now we're going to look at implementation here. Now the key thing here is not the implementation itself, because there are actually different ways to implement a stack. And as we say, we focus on abstraction. So what we care about is the operation of the stack. But on the other hand, having said that, we want to bring across the idea that when you use a data structure, it's useful for you to know what is going to be the operation of those data structures, so that you can characterize the complexity. Because you might come up with an algorithm like this, and you're trying to say, okay, what is the complexity of this? Now, when you talk about the complexity of this, you need to talk about the complexity of the stack operations. Because when it's doing push and pop, but you don't know how many operations is happening inside, you might underestimate or overestimate the number of steps that you're going to take. Now, let's take a look at one simple example here. Now, we're going to pretend at first that we have a stack, and we're going to use a list or an array to store this stack. And we can designate one specific position in the array to be the top of the stack. And let's suppose that the top of the stack is the index 0. So if the top of the stack is index 0, now if you currently have orange and gray, where orange is the top, gray is below, so you will have the following array where orange is the top, gray is below. Now when you push a new element in, for example kiwi, then it's going to go to the top of the stack. Now going to the top of the stack, it means that when it goes into the array, it needs to go to position 0. Now, but position 0 is now occupied by the previous top, which is orange. So then what we need to do is to make room. And to make room, we need to shift everything down, which in this case, you shift orange and gray down, and then you can make space for kiwi to go to the first position. Which means that the complexity of this is going to be O(n), because you need to shift. How many things do you need to shift? You need to shift n things if n things existed in the stack. Now, pick is to take a look at a specific element which is currently at the top. And the top is 0, so in this case I just need to read what is at 0, and that returns the top. So the complexity of this will be O1, because all you need to do is just to go to index 0 and return the element there. Now, pop on the other hand is to remove an element out. So if the current top is kiwi at index 0, when you remove it, you want to take kiwi out so that the stack doesn't have kiwi anymore. But now index 0 is empty, and index 0 is designated to be the top. So then what we need to do is to shift everything up. And if there were n elements there, we need to shift n-1 elements up. And in that case, that's going to be O(n). So you have O(n) push, O(n) pop. Now, can we do better than O(n)? How do we do better than O(n)? Yes, how?
Can we just say the last index is the top? Then we just append and just pop the last index.
Yeah, you can do that. So in that case, what's going to be the push?
The push is one.
Yeah. So if we, instead of putting the top in index 0, which is an arbitrary choice anyway, we decide that it's going to be 0. We can instead decide that anything that is at the top is going to be at the end. So So when we push, we put it at the end. Nothing needs to shift, so it's O1. When we pop, we take up from the end. Everybody still stays put. Then it's still O1. So actually, stacks and queues, you can still do it in O1 just by having a judicious choice of where to put the top of the stack. Alright? Now we're going to take a look at stack and recursion. And here we actually want to clarify a particular point. And the point is that, recursion, how is recursion actually executed? Recursion, once you enter the operating system, or even at the compiling stage, it might actually come into the function call stack. And the function call stack is going to help the operating system to determine what is the sequence in which we're going to solve a certain problem. So here, we will show how is it that for a given recursive method, you can actually convert it and make the stack operations explicit so that we can get a sense of how this was actually done in terms of the runtime. Now let's take a look at this particular example. So in this case, you have a Fibonacci recursion, and it's going to go through the function calls in a particular sequence. So for example, so you have this Fibonacci. These are the base cases, right? So 0 and 1, and then you make two recursive calls, n minus 1, n minus 2. Now let's take a look at Fibonacci 4, right? So Fibonacci 4 is not a, 4 is not a base case, so we're going to make two recursive calls to F3 and F2. But when it's calling F3, now we have to wait until F3 is done before we can proceed with calling F2. So then we're going to start another recursion that starts from F3, and F3 itself will call F2 and F1, but it needs to wait for F2 first before it can actually return and process F1. And F2 is going to call F1 first and then F0. So which means so far, if we look at the sequence in which this is done, this is number 1, this is number 2, it's number 3, number 4, number 5, in terms of the sequence in which we are executing. Now, once we are done with F0, it goes back to F2, then F2 goes back to F3. Now, F3 can then call on F1. Oh, sorry, F2 still has F1 and F0, correct? Yeah, F1 here. So F1 then is going to be number 6. Now, F2 and F1 done, it will go back to F3. F3 is going to go back to F4. Now F4 can now go on to the second branch, which is F2. So which in this case, F2 is going to call on F1 as well as F0, which means that in terms of the sequence, is going to be F2 here is going to be number 7, number 8, number 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a sequence here. 4, 3, 2, 1, 0. Then we have 1, then 2, 1, 0, which is exactly the sequence here when we are printing the n as we are calling it. So essentially the recursion is going to proceed in a particular sequence. Now we can convert something like this into a form based on a stack that is not recursive. Now that form is going to look like this. Essentially we remove the recursion. Instead we rely on the stack to keep track of the sequence. So we create a stack, we push the n in, and then we enter into a while loop for as long as the stack is not empty. If they are base cases, which are 0 and 1, we just compute the results. If they are not base cases, then we need to push new reduction cases into the stack. Now, when you push the reduction cases onto the stack, you realize it's n minus 1 first, then n minus 2. So when you push into the stack, it has to be n minus 2 first, and then n minus 1. Because the next time round, when you pop, you're going to get n minus 1 first. Now, if you do this, then essentially you have a different implementation of Fibonacci, no recursion, based on a stack. But if you look at what is the top of the stack at any time, which in this case the top of the stack is at the end. So 4, 3, 2, 1, 0, which is the same as 4, 3, 2, 1, 0 here. Then we have 1, 2, 1, 0, which is 1, 2, 1, 0 here, which is, so in this case, the stack base Fibonacci and the recursive Fibonacci are going to essentially undergo the same sequence of operations. So this is only to bring up the point that recursion essentially can be done using a stack. It's just a different way of iterating over the elements there. Alright, so now the other example, you can do the same with binary search. We're not going to do this, but here in this case, you have things that you basically push and pop from the stack to mimic the operations of the binary search. Alright, now there are some class exercises here, but I don't think we need to break to do this because I think we can do it on the spot. These are relatively simple. We just want to clarify what it means to do things on a stack. Now let's say you're given a sequence, right? So what's going to happen here? So this creates a new stack. So okay, so let's say we create a new stack. So when you draw a stack out, always indicate where the top is, because some people like to draw stack horizontally. Some people like to draw stack vertically. In any case, always indicate where is the top. So let's say this is the top. So when you push 1, then 1 goes into the stack. You push 3, then 3 goes into the stack. Then you pop. You pop means that you take anything that is at the top of the stack, which in this case 3 will come out and it disappears from the stack. So then we push 4, pop, so 4 is going to come out, disappears from the stack, then push 2. So then your stack will contain 2 and 1. So previously 3 and 4 have been popped out. Now for this one, so let's say this is the top. So you push 60, you get 60 in. Now peak, you will return 60, but you don't remove it, so it will stay put. Push 34, pop means 34 is going to come out. Push 72, push 44, 86, so pop is going to take out 86. Then pop again is going to take out 44, push 59, so in the end the stack is going to have 60, 72, 59, and 59 is the top of the stack.